So first I'm going to talk to you about uncertainty and errors. In measuring, there is always some intrinsic range of uncertainty. You can only say that something is for sure within the range that you are measuring in. This might bring you back to the evaluations that you've done in your experiment write-ups in the past. The whole point of an evaluation is to stay up until where you are sure that your conclusion is correct. Well, the fundamental fact is that you are limited by your measuring device. That's always going to be a limit to your conclusion. Within the range of my measuring device, my conclusion is certain. But if I include ranges outside of mine, and if I use a different device, there is always a possibility that you could offer a different set of results. No matter how hard we try, even with the best measuring instruments, it is simply not possible to measure anything exactly. For one reason, the things that we can measure do not exist as perfect exact quantities. There is no reason why they should. Every measurement that we take is always an approximation limited by the range of our measurement device. If I say I'm going to measure something with a ruler, I can make a very exact measurement to the nearest millimeter, or in this ruler you have to the nearest half millimeter. But within the range in between, if you have a measurement which lies in here in this space between one interval and the next, you are unsure. You do not know exactly where it lies in between. So that's what we refer to as instrument uncertainty. It's an indication of up until what point can we definitely say the number is true. There is a real theory of knowledge aspect here. As it says here, one aim of the physical scientists has been to give an exact picture of the material world. One achievement of physics in the 20th century has been to prove that this aim is actually unobtainable. It is in the sheer nature of science to question and to exploit the doubt, to ensure that science is ultimately able to be replicated, conclusions are firm, and that this uncertainty is constantly questioned. Can scientists ever be truly certain of their discoveries? Well, experimentation will eventually get to a point where some discoveries can be certain. But it's a complicated subject. In scientific discourse, it conveys the idea of uncertainty, conveys the degree to which something is known. So when we talk about the uncertainty in a measurement, what we're saying is how sure we are that this is the true value. But the very reason that we are discussing a quantity should mean that we have a strong indication that we're in the right direction. Uncertainty is a very scientific concept, and it's numerical and it's quantifiable, and it usually relates to a number or a percentage. Unfortunately, in the vernacular, what we mean by that is in everyday use, the word uncertainty conveys a sense of not knowing. The difference is subtle but very important, and ultimately has been exploited over the last few years by deniers of firm scientific conclusions, which each have their uncertainty. There is a 97% confidence in the fact that climate emergency is imminent, 97% being the number or the percentage of scientists that firmly believe that human activity has caused it. But that 3%, which is a mathematical indication of the scientific community that is questioning it, has been leapt upon by climate deniers. Similarly, with the panic over G5 towers and vaccine phobia, which is raging, this idea of uncertainty now has a massive social impact. Anyway, back to physics and back to hard numbers. In physics, whether we're measuring the resting rate of an adult male or the age of a historical artifact, or the force acting on an object, or the distance that can be calculated through the motion of an object, we do not have exact values. We always have a range of values when we are doing this experimentally. That range of values is quantified by uncertainty. That uncertainty might be due to the instrument uncertainty, and sometimes it's an uncertainty due to other factors. Perhaps your heartbeat doesn't give you an exact predictable value because something in your activity, you happen to be watching something that's exciting. There's an external influence which is affecting the predictable aspect of your heartbeat. The same with forces. You're predicting the flight of an arrow, but the wind blows. These are extra factors that, unless you consider them in your computation, they're always going to provide some uncertainty. So what you've got there is uncertainty with your measurement, and you also have uncertainty because of extra factors. In any case, this uncertainty can be expressed as the probability of obtaining a certain value. And what we have are probabilities distributed about some certain mean. We don't have to go into this probability aspect for the IB, but I know that the cognitive reading does refer to it, so I'm bringing it up here. We're going to consider uncertainty simply as an expression of a measurement, and then we'll consider the extra factors later. The objective of today's lesson is to learn how to write down a reading from an instrument and to express the uncertainty depending on that reading. When you are taking a reading from an instrument, you must use the number of significant figures given by the instrument. Important point. Now, how do we know? Those significant figures will give you an indication of how sensitive the instrument is. We express the reading and the uncertainty in the following form. You will always, from now on, write down your measurements like this. You will have the reading itself and you will have the uncertainty. Both are important aspects. In this stopwatch here, we can read that it's 5 and a bit. Now we're going to express that in a bit accurately. The way to express the absolute uncertainty, which is the uncertainty of the instrument, depends if it is a digital instrument or if it's an analog instrument. This stopwatch is an analog instrument. An analog instrument gives you an entire range of possibilities. It's constantly measuring through a continuous range of values. So, anything that has divisions like this one and a dial that can literally stop anywhere in between. This voltmeter here is another example of an analog measuring device. Now, the rule for an analog measuring device is half the smallest division on the measuring instrument. So you find the value of the smallest interval, which in this case you can see is 20 volts. If you want to stop the video and check, 20 volts. Then half the smallest division would be 10 volts. Let's go back to our original instrument. The reading here is somewhere between 5 and 6. So you can see that your reading is 5.5, but you don't know that 100%. You now need to state your uncertainty. And your uncertainty is, because it's an analog instrument, is half the smallest interval. One interval on this clock is 1 second. Half an interval is 0.5 seconds. And so what you're saying by this statement is that your answer could be 5.5 plus or minus 0.5. It could be anywhere between 5 and 6, basically. Now, this has an important consequence on significant figures, right? Another very, very important point. You only use the number of significant figures given by the instrument. Here, our instrument can give us up to 1 decimal place or 2 significant figures. That's all we write. We would not write 5.50 or 00. We only write what the clock or the watch, can give us. And that is actually given to us by the uncertainty. The uncertainty will dictate the number of decimal places in your reading, and so will give you an indication of the significant figures. This will be easier to understand when you start measuring things. So how do we find the uncertainty in a digital instrument? Digital instruments are a little bit simpler. Because they don't give you a continuous range of values, they simply give you one value or the next, but nothing in between. There is no way for you to judge what's happening between 49, 50, 51. Those are unknown to you. So what we're doing is we are using plus or minus the smallest division. So here we can see that the smallest division is 100th. The same with this instrument here. It's giving you the smallest possible interval of 1/100th of your reading. So the value here would be 95.80. Why is that 0 there? Because the instrument can give us that information. And the smallest interval of uncertainty is plus or minus 0.01. I'd like you to try some of these readings at home or at school. Use a ruler to measure the dimensions of your page. Have a look at the ammeter and voltmeter readings and see if you can decide what the uncertainty is. Same with the thermometer, stopwatch and protractor. If you do a few of these, we should be okay. Similarly, if you want to try this exercise and check your answers.